Hi, this is Pat Kelly. In this video, we're going to finish the problem we started in the previous video. All right, little pat on the back so far, but we continue. Part B, inflection points. You know this as well, just like you knew relative extrema. In order to find inflection points, in order to find places where there might be inflection points, you need the second derivative. So, G double prime. And now I'm looking to differentiate this expression, okay? Notice it's actually a product rule. Okay, so I'm looking at that multiplication here, and I'm going to follow my product rule template. And my template is differentiate the first chunk of it first. So I'm going to differentiate this guy, which is minus 1 over square root of 2 pi, because that's a coefficient. Here's my exponential. As I differentiate that, it always just spits itself right back out without changing. And then multiply by the derivative of that exponent. Here again, I've got that minus sign. I'm going to shunt that all the way out here. There is a minus sign. I'll just make that a plus sign. I'll try to switch colors on you again in case you look back at this. It was a minus from what I carried down below, but then it's now a plus because I just differentiated this minus sign here. And then that 2 comes in front, divides with that 2. X minus 2 drops down to the 2 power, drops down to the 1 power. Then I'm multiplying by the derivative of what's inside those parentheses, but again, the derivative of that's going to be 1, so I'm not going to write that. Then I have to remember I'm in the middle of a product rule, so the second factor of the function remains the same right now. That's an x minus 2. So I'm actually going to square this because I'm multiplying this x minus 2 that I just wrote times this x minus 2. Okay. Still in the middle of a product rule, so I need a plus sign. And then the first chunk of this left alone, so that's going to be the minus 1 over square root of 2 pi. All right. I'm going to put parentheses just because of the plus and then the minus. This e still, I'm leaving it alone, part of the product rule. X minus 2 parentheses squared divided by 2. All right, and product rule, I'm now multiplying by the derivative of this second chunk, x minus 2, but the derivative of that is just 1. Right, so I'm actually good. I'll close those parentheses there. So this looks like my second derivative, and I'm going to clean it up just a little bit here. If I look to see what I might be able to factor out, I'm going to factor out a minus 1. I forgot, that actually changed to a plus. Let's factor out the plus 1 over the square root of 2 pi. And what I see as being the same between these two terms is that fraction that I just wrote, but then also this exponential expression. So e raised to that minus x minus 2 parentheses squared divided by 2. I'll use square braces here now just in terms of if I factored that stuff out, what's left on the inside. So this is all accounted for. All I would have is x minus 2 parentheses squared from the first term plus, and I'm actually going to use this, I'm going to include this minus sign here, minus, and everything here, each factor got pulled out, so all that's left is a 1. All right, that's my second derivative. Now, why did I do that? To try to find inflection points. Let me try to find a little bit of space over here to look for inflection points. And inflection points, you know, can occur at the places where the second derivative either doesn't exist or where it equals 0. I'm trying to say the doesn't exist part first because I'm going to dismiss it pretty quickly like I did before. This expression for the second derivative doesn't have any issues, no division by 0. So there's not a concern about it not existing. All I'm worried about here for inflection points, or where the inflection points might occur, is where the second derivative could be 0. But here again, I can dismiss a few things because this constant factor can't be 0. Here's that exponential expression again. That won't ever equal 0. So all I'm worried about is my square braces. That's the only thing that's going to make this 0. So I'm looking to solve just a little bit of algebra. X minus 2 parentheses squared minus 1 equals 0. And I'm actually setting that equal to 0 to solve it. All right, so x minus 2 parentheses squared equals 1. X minus 2 equals plus or minus 1 if I square root. X equals, I'll add 2 to each side. So I get 2 plus or minus 1. X equals 3 or x equals 1. All right. Now, I don't know if those x values are going to lead me to inflection points yet. What I need to do is this type of number line work again, where I put those possible locations for inflection points on the number line and then test my intervals. Alrighty? Okay, and again, I'm not going to jump to a calculator. I can use my same thought process. Anything to the left of 1, so you pick a 0. This chunk is the constant chunk, always positive, right? This chunk, also exponential, we said, always positive. So all I'm really worried about in terms of whether the second derivative is positive or negative is what's going on inside this chunk, my square braces. So I picked 0, let's put a 0 in. 0 minus 2 is negative 2, but squared is 4. 4 subtract 1 is 3. All I care about is that it's positive, so plus, plus. I only use double pluses just to make it look a little bit different than my number line for the first derivative. Between 1 and 3, I'll pick a 2. Same thought process, positive, positive. Plug in a 2 right here. 2 minus 2 is 0 squared, but then subtract 1. That's going to be minus, minus. Third interval, pick a 4, positive, positive. Put a 4 in here, squared. 4 minus 2 squared, 4 minus 1. That looks like plus, plus. All right. Now in terms of inflection points, those come from where the function changes concavity. This number line tells me that this interval is concave up, this interval is concave down, this interval is concave up. So those x values are actually pointing toward inflection points because the graph does change inflection. Does change concavity. So let's get our answers for the inflection points. I'll just write them over here. I say get our answers because even like we did with the relative max over there, you need both the x and the y. So I'm going to have 1 comma. Let me leave some space. Well, I'll go right below. And then 3 comma. And I need my y values, which are going to come from plugging these x values into the original function. So let's grab 1, the value of 1, and plug all the way up in here. 1 minus 2 is negative 1, but squared is positive 1. So I'm looking at an exponent up there of minus 1/2. And I'm going to write it just like that. I have my coefficient 1 over square root 2 pi, and then e raised to the minus 1/2. Close the ordered pair. My second y value, I'm plugging in a 3. 3 minus 1 is, 3 minus 1 is 2, I said that wrong. 3 minus 2 is 1, squared is 1, but there's a minus in front. It ends up looking exactly the same as the y value we just calculated. E raised to the minus 1/2. Close that ordered pair. All right. Okay. The third part of the problem is to confirm with a graphing utility. So grab a graphing utility. I have mine handy here. In your y equals, you're going to have to enter this original. It's up here in pink for me. Get that to behave on your graphing utility. I'm going to give you some advice on the window settings to make this look good. My x min was negative 1. My x max was 5. My y min was 0. My y max was 1, and then I'm ready to graph. Has to think for a little bit, maybe. Looks like a bell curve. It should. You might have recognized that at the beginning of the problem. You can see the peak of it, the top of it, and your graphing utility should have some kind of calculate feature where you can find a max, just to verify our answer. Lower bound of 1 is good, upper bound of 2 is good, or a little higher, even guess of 2 works, though. And I'm getting my maximum at an x equals 2, a y value of about 0.4, which is, let me come over here, what this y coordinate looks like as a decimal. Okay. In terms of verifying the inflection points, what we have listed there, the last work that we just did, I'm looking at the graph and seeing that it actually looks like it changes concavity about halfway up the curve and halfway down the curve. And that's going to be at x equals 1 and x equals 3. It should look like it's actually changing in the way that it's bent. All right? Okay, a lot of work. Practice some on your own.